gravitational potential energy. So we will take the different cases for gravitational potential energy. The first important thing you need to remember about potential and potential energy. This is the point number one. You need to know potential and potential energy potential energy are not absolute. You may have come across this idea before, because you measure the potential and potential energy against a standard reference point. So these quantities are measured or defined quantities are defined with a standard reference. Standard reference. Now let us come to gravitational potential energy. We have calculated the gravitational potential energy close to the surface of Earth. You have the expression here. Gravitational potential energy close to the surface of Earth of, you already know the expression. It's given by G P E is equals to mg h. In this expression, h is the height from the surface of the Earth. So in this case, the reference point is the surface of Earth. So the assumption is that there is the assumption because this is the reference point you fix. Gravitational potential energy on the surface of a body or on the surface of the Earth, on the surface of Earth for a body is equal to 0. So the standard reference is the surface of the Earth. Now this is how we do it in case of uh, points close to the surface of Earth, because we assume that the gravitational field strength is uniform close to the surface of Earth. But when we consider two point masses sufficiently apart, this relationship cannot be used. In that case, we will have to use the uh, relationship for the gravitational force as described by Newton. Just let us see how it works out. So, gravitational potential energy of a system of two point masses. Two point masses. So instead of point masses, you may also consider two perfectly spherical bodies. The relationship would remain mostly the same. So we will see the relationship. So instead of point masses, we assume two spherical bodies. So we have two spherical bodies here. Let's have a picture here. So this is the first body. Okay. Then We have a second body in here. So we need to find out the gravitational potential energy of this system. We need to find out the gravitational potential energy of this system. So this the first body we take it as capital M as the mass. For the second body, the mass is small m, and the separation between the two bodies is r. Obviously, now how do we define the gravitational potential energy of this system? Now you can say that this is the gravitational potential of m in a gravitational field of capital M. That's fine. Or you can say this is the gravitational potential energy of capital M in the gravitational field of small m. But the best way to put it is to say the gravitational potential energy of a system of two bodies. So instead of point masses, we have used two perfectly spherical bodies. So we assume that the gravitational force between these two bodies acts along the line joining the center of masses of the two bodies. So to work out the gravitational potential energy, we use the standard definition. So what is the standard definition? You will have to bring the small mass m from infinity to this point, infinity to this point, along any path without any acceleration, and how much work is done, that will be the gravitational potential energy. So this point we may mark as infinity. So we are bringing this body along a straight line to make it easy for us the calculation. So we can just write, first we'll write the definition, so let's put it in a different color. uh, what would I use? Probably this. No, not so good. No, no, right. Okay. Gravitational potential energy. By definition, you can write. Now, the work done in bringing the two bodies in this case, bodies from infinity. So, from infinity to a separation or to the distance are from each other. So this is the definition we are going to use. Earlier, when we have defined gravitational potential, it's the work done in moving 1 kilogram mass from infinity to a point. But when we talk about the gravitational potential energy of two bodies or a system of two bodies, we define it as the amount of work done in moving these two bodies, which was initially infinitely apart. Now they are bringing together to a separation of r. This is the idea. And now we can assume that take one of the bodies and move them from infinity to all the way to the point. We call this point P if you wish. It makes it easy for you. And we can just work out the standard relationship. What is it? Gravitational potential energy, GPE in this case, GPE is equals to negative integral infinity, this would be infinity, not alpha, infinity to the separation of F. FG stands for the gravitational force between the two bodies, and you integrate it using FGTR. This is the expression. In this case, Fg is the Newton's equation. Fg in this case is given by negative. Negative sign only indicates the direction. In this case, direction is separately important. We can do it without the directional factor. But since I have chosen to include the direction in all these derivations, I continue with that, not compulsory. There are many different ways you can interpret this. So now you substitute the value and do the integration within the limits. So when you do that, you will get G P E is equal to of the two system of bodies negative integral infinity to R. Instead of FG we can write negative G M M over R square dr. The negative and negative cancel out. When you integrate Gm over R, you will get minus Gm by R. So this is equal to negative negative G M M over R, and we have the limits. The upper limit is R and the lower limit is infinity. So this is R and this is infinity. So when you apply the limits into this equation, you will get the expression GPE of the system, gravitational potential energy of the system, is given by negative G M M over R. So this is the expression for the gravitational potential energy of a system of two point masses or two perfectly spherical bodies. So you should not get confused this with mgh. The equation mgh is applicable only close to the surface of a planet or the surface of the earth. So the reference point where the gravitational potential energy is zero are different in these two equations. So on a celestial scale, you must always use this equation. And obviously, the negative sign implies, what does it negative sign imply? The negative sign implies, we already know that, negative sign implies that two body system is a bound state. Of course, in gravitation, the two body system in gravitational field is a bound state. Two body system is a bound state. Bound state. Also, you can interpret this as that this is the consequence of gravitational force is attractive, because this comes into effect because the gravitational force is attractive always. Oh, sorry, gravitational force is attractive. So now you can have a very simple assignment, uh, a simple question which you can try out. You can get the values from the internet. Let's say a simple question. I'm not going to work it out. You should work it out on your own and see what value you get. Now, find the gravitational potential energy of a person of mass 60 kilogram on the surface of Earth. Surface of Earth Now, to work out this, you may require the mass of the Earth, and you also require the radius of the Earth, and you should assume that this is perfectly spherical. And you can substitute the values into the expression, and you will get the value of the gravitational potential energy. Obviously, you will get it negative. So that's it for today.